All right, let's dive into one of the most powerful and, let's be honest, controversial technologies on the planet, nuclear energy. We're going to break down how we get so much power from a single atom, and maybe more importantly, how we keep it all safe.
I mean, seriously, think about that for a second. It sounds like something straight out of science fiction, right? But that's the wild reality of nuclear fuel. This unbelievable energy density is exactly why we're so fascinated by this technology. So how in the world do we get all that juice out of something so tiny? Well, it all comes down to a process that is honestly both elegant and just unbelievably powerful.
Yeah, the secret is all happening at a scale you can't even see, inside the atom. The engine that drives this whole thing, it's not made of gears and pistons. Nope. It's a natural phenomenon, a fission chain reaction.
So, nuclear fission, what is it really? At its heart, it's just about splitting things apart. Think of a big, clunky, unstable atom like uranium-235. It's just so jam-packed with stuff that it's basically wobbling, just waiting for a reason to break up. When we give it a tiny nudge, it shatters into smaller pieces, and in that process, it releases a massive burst of energy. But here's the really clever part. It's what happens next that makes it so powerful. This is where that cosmic dominoes idea comes into play, and it's a perfect analogy. So picture this. We kick things off by flicking just one tiny particle, a neutron, at a uranium atom. Bam, the atom splits. It releases a burst of energy, sure, but the key thing is it also releases a few more neutrons. Those new neutrons then fly out and hit other uranium atoms, which also split, releasing more energy and even more neutrons. And that is the chain reaction. It's this beautiful, self-sustaining atomic pileup that generates the incredible, intense heat we need. Okay, so we've got this incredible chain reaction going. That's great, but how do we actually control it? And more importantly, how do we turn all that atomic chaos into the electricity that powers your phone? Well, that's where the nuclear reactor comes in. I love this quote because it just cuts through all the complexity. Because really, for all of the mind-bending physics we just talked about, a nuclear power plant is basically a super, super high-tech way to do something we've been doing for centuries: boil water. So, step one is all about the heat. Deep inside that reactor core, the chain reaction we talked about is happening, but it's being carefully managed. Think of it less like an explosion and more like a steady, controlled burn. It's like an atomic furnace, just humming along, generating an unbelievable amount of heat. Okay, so we've got all this heat. What do we do with it? Simple. We use it to boil water. A lot of water. This creates super high-pressure steam that just blasts through a massive turbine, spinning it like a pinwheel in a hurricane. And just like that, we've turned atomic energy into good old-fashioned motion. And for the final step, that spinning turbine is hooked up to a generator. Basically, through the magic of magnets and copper wire, the generator converts that spinning motion into electricity. And that's it. That's the electricity that gets sent out on the grid to light up our world.
Okay, but let's talk about the elephant in the room. We're talking about harnessing the power of the atom here. That's some serious stuff. So the big, obvious question is, how on earth is this kept safe? How do you keep all that power contained? Well, the answer is, you build a fortress. The whole philosophy behind nuclear safety comes down to this one core idea: defense in depth. What that means is you never trust just one thing to work, ever. Instead, you build layers upon layers of safety systems, all independent of each other. It's not just having a plan B, it's having a plan C, D, and E. It's backups for your backups. And that philosophy starts with the physical stuff you can actually touch. First, the fuel itself isn't a powder or liquid. It's baked into these tough little ceramic pellets designed to trap the nasty byproducts right inside. Then, those pellets are stacked into long metal rods. Those rods, they go inside a giant, super thick steel reactor vessel. And that entire thing is then sealed inside a massive containment building. You see? It's like a Russian nesting doll of safety. Each layer is another wall in the fortress. And let's talk about that final layer for a second, the containment building. This thing is an absolute beast. We're talking about 4 feet, that's 1.2 meters, of steel-reinforced concrete. These structures are engineered to handle pretty much anything you could throw at them: massive earthquakes, even a direct hit from a jetliner. All right, but no technology is perfect, right? To get the full picture, we absolutely have to talk about the leftovers. And for nuclear power, the biggest challenge, the thing everyone talks about, is the waste. Now, it's really important to understand that nuclear waste isn't just one thing. It's actually broken down into different categories. Most of it, by volume, is what we call low-level waste. Think tools, gloves, protective clothing, stuff that's been near radioactive materials but isn't intensely dangerous. The real issue, the one we need to solve, is the high-level waste. This is the used fuel itself from inside the reactor. There isn't a lot of it, but man, it is highly radioactive.
So what's the plan for this stuff? Well, the global scientific consensus right now is a strategy called deep geological storage. The idea is to seal the waste in incredibly tough containers and then bury it deep, deep underground in rock formations that have been stable for millions of years. The goal is to keep it completely isolated from the environment until its radioactivity naturally fades away over a very, very long time.
So there you have it. You've got this incredible atomic engine, a surprisingly straightforward way to boil water and make electricity, and this fortress of safety systems, all weighed against this really profound challenge of what to do with the waste. It's this tension, right, between incredible power and incredible responsibility, and that really is the core of the whole debate. It leaves us with a big question. What role should atomic energy play in our future?